Swayam Prabha. Digital India. Educated India.
Hello, so welcome friends, welcome to the course Introduction to Sampling Theory. You may recall that in the last couple of lectures we had talked about the ratio method of estimation, and you can recall that one of the basic objective in introducing the ratio method of estimation was that we wanted to use some auxiliary information from outside the sample, and we expected that this is going to improve the estimator for the population mean. So, what we did, we had chosen a variable that we had called as an auxiliary variable in such a way which is correlated with the variable under study, and then we had used the information on that auxiliary variable to improve the estimator, and we had improved the estimator of population mean that we had considered as a sample mean. So, we improved the sample mean by taking the ratio of y bar upon x bar, that is the sample means of y and sample mean of x. Yes, we had to assume that capital X bar, which is the population of the auxiliary variable, the mean of that population is known to us. So, that mean can be known to us from some external sources. When I started the ratio method of estimation, then I had given you a basic idea that our main motive is to use the auxiliary information. So, in order to use the auxiliary information in the estimation procedure, we had introduced two types of estimation method. One was ratio method of estimation and another was regression method of estimation, right. So, now from this lecture we are going to talk about the regression method of estimation, and you will see that this is also a method for estimating the parameter, and our parameter of interest is an estimator of that parameter population mean, right. So, now once again I would like to caution you all that regression method of estimation is also an methodology for the estimation of the parameters. This is not the method of sampling, and that you have now realized in the case of ratio method of estimation that you already have the samples. You had the paired samples on the variable under study and the auxiliary variable, and you have used it for improving the sample mean to get a better estimator, and you have seen that the success of a ratio estimation depends that how good is your auxiliary information. So, for that we had derived the conditions which are based on the correlation coefficient between the variable under study and the auxiliary variable. So, now in this lecture we will continue on the same lines, and for you can think simply as we have discussed the ratio method of estimation. Similarly, now we are going to discuss one more method of estimation, regression method of estimation, right. So, let us begin our lecture, and in case if you want to download the slides of this lecture, you can go to my home page, and from there you can download the slides in the PDF format. And I have uploaded these slides at this address at my home page. The address is home.iitk.ac.in /shalab/sp, right. And if you have any problem in reaching to this address, then you can also scan this QR code using any application in your phone, and you will arrive at the same address. And still if you are facing any problem, then I would suggest you that you just use any search engine on the internet, type my name SHALABH and my institution IIT Kanpur, and you will reach to my home page. From there you can download the slides. Right. So let us now first try to understand what is this regression method of estimation and why are we going to use it. So before I move forward, let me tell you that this regression method of estimation can be introduced from 2 points of view. One is that if you try to remember, in the case of ratio method of estimation, we had taken the ratio of sample means of y and x, the steady variable and the auxiliary variable. So a basic idea comes, if I can consider the ratio, why not I can consider the difference also. So that is why there are two approaches to obtain the regression estimator. I will try to show you here both the approach, and the second approach is based on the principle of least squares, that you try to assume a linear model and can you try to obtain least square estimates of the parameter by minimizing the sum of square due to random error, and you will get the same thing. So I will try to illustrate here both the things, and sometime you will see that in the books this estimator will also be called as difference estimator. Right. So now let us try to understand all these things. So in the case of ratio method of estimation, you can recall that we are trying to use the auxiliary information, and this auxiliary information is obtained in such a way on a variable which is correlated with the steady variable. And what was the objective? That we wanted to improve the precision, and which is going to result in the improved estimator when the regression of y on x is linear and passes through origin. You can recall that we have done condition when ratio method of estimation is going to be optimum, and at that time also I had shown you that in case if you have a set of paired observations which can be plotted like this, and in case if the regression line is passing through the origin, then this ratio estimator is going to work better. Now there is another question. Suppose now the regression line is not passing through the origin, but it is passing somewhere else like this, where this intercept term is not equal to 0. Now what to do? Because the regression line of y on x may not always pass through the origin, right? So under such type of condition, it is more appropriate to use the regression type estimator to estimate the population mean. Right. So now there is a rule of for you to decide between the two methods of estimation, that which one would you like to choose. You just try to take your paired observation, try to plot them, and if you feel that the regression line which can possibly be fitted to that data, if that appears to be passing through the origin or it is very close to origin, then ratio method of estimation is better to use. And if not, then regression method of estimation is better to use. Right. So if you try to recall what we did, that in the case of ratio method of estimation, we had considered the sample mean of y bar, and then we had improved it by taking the ratio of y bar and x bar, and then we were trying to improve it. Right. And in this process, what we had obtained, that your estimator became y bar upon x bar into capital X bar. So now if you try to look, can I write this thing as say x bar upon capital X bar upon a small x bar into a small y bar? So don't you think now this looks like as if we are trying to consider the sample mean as an estimator of the population mean, and we are trying to multiply it by the ratio of population mean of the auxiliary variable and sample mean of the auxiliary variable. Right. And here the advantage is that both this small y bar and small x bar, they are going to be an unbiased estimator of their respective population means. Means expected value of a small y bar is equal to capital Y bar, and expected value of a small x bar is equal to capital X bar. Why? Because we are assuming that the observations on the paired sample are also drawn by simple random sampling. In case of the ratio method of estimation, the conventional estimator, which is your here sample mean, a small y bar, was improved by multiplying it by a factor capital X bar upon a small x bar, that is the ratio of population mean of auxiliary variable and the sample mean of the information on auxiliary variable. And where this small x bar is going to be an unbiased estimator of the population mean capital X bar, and which is the population mean of the auxiliary variable, right. So now here if you try to see, you are trying to take a ratio. So now another idea is that can we consider the construction of an estimator based on difference? So let us try to see how. So if you try to see, you have taken here the ratio of capital X bar upon a small x bar. So now we are going to take the difference, x bar minus capital X bar. And if you try to see here, means if you try to consider this quantity small x bar minus x bar capital X bar as an estimator, then the expectation of this quantity is equal to 0. Why? Because you are trying to draw the sample by SRS WOR, or in general I will say simple random sampling. So now we use this concept and we try to propose an estimator with, which is of the form like this one, small y bar plus mu times small x bar minus capital X bar. Here this mu is any actually constant. So now what I will try to see here, that mu is going to be unknown quantity. So now we have to find out the value of mu such that this new function becomes an improved estimator of the population mean. So if you try to see, since you are trying to consider here a linear combination of sample mean small y bar plus mu times small x bar minus capital X bar. So if you try to take its expectation, still the expectation of this quantity is going to be the same as the population mean of y. How? So let us try to first indicate this estimator as say y bar hat star. So if you try to take the expectation here, then it will become here expected value of y bar plus mu times expected value of x bar minus capital X bar. So this quantity is equal to 0 and expected value of small y bar is equal to capital Y bar. So you will see that this is now already an unbiased estimator, and this is how we have constructed it. The only thing is now, if I can find out the value of mu such that the variance of this y bar star hat is minimum, then I am done. So that is what now I am going to do. I try to find out the variance of this estimator. So the variance of this estimator will become variance of a small y bar plus mu square times variance of a small x bar plus twice of mu covariance between x bar and y bar. And now in case if I try to differentiate it, this equation with respect to mu and put it equal to 0. So essentially you are going to use the principle of maxima minima actually. Then if you try to put it equal to 0, then the value of mu comes out to be like this, minus times covariance between x bar y bar divided by variance of a small x bar. And now since you have used here the simple random sampling without replacement, now you know the expression for the values of this covariance and variance. So I try to substitute these values here. So covariance between x bar y bars we had found as capital N minus small n divided by capital N into small n Sxy, and this variance of a small x bar will become on the similar line capital N minus small n divided by capital N into small n times Sx square, and I try to take the ratio of the two. And if you try to see it, this term get cancel out and we get here minus times capital Sxy upon capital Sx square. Yeah, both these terms capital Sxy and Sx square, they are the same what we have used in the earlier lecture. Okay, so now this is what you have to keep in mind, that the form of the mu is coming out to be minus times Sxy upon capital Sx square. Now in case if you try to observe the structure here Sxy upon Sx square here, then in case if you have done any course on regression analysis, you can identify it very easily. That in case if I try to take a linear equation, something like y equal to x beta plus epsilon type of thing, where y is your steady variable, x is your auxiliary variable or independent variable, and alpha and beta are the regression parameter, and epsilon is the random error, right. Then in case if you try to minimize the quantity summation epsilon I square I goes from 1 to n on the basis of n pairs of observations xi yi I goes from 1 to n, then the value of beta will come out to be like this. So, this is the value of the slope parameter in the population. So, you can imagine that if you know the entire population and if you try to find out the true line, true relationship between x and y, then the slope parameter will come out to be Sxy upon Sx square, and I will try to show you later on that when we try to prove it, this will come out to be the same thing. But here I am just telling you so that those students who have this idea, they should believe that well they are going to get the same thing. Okay. So, now we try to use the principle of least square on such an equation, then how will you obtain such a thing, right. So, what we try to do here, that first we try to consider a linear regression model which is of the type y is equal to beta 0 plus beta 1 x plus epsilon. So, y is here your steady variable, right, there is no problem in understanding this thing, and small x is your auxiliary variable, or in the case of regression analysis this is called as independent variable, right. And the meaning of this relationship is this, that there is a response y which is going to depend on an independent variable x. For example, in case if you try to see output of a yield depends on the quantity of fertilizer. So, y is your yield and x is your quantity of fertilizer, and epsilon is your random error that is involved in the observation, and this random error does not allow all the observations to lie on exactly on the straight line. So, you have a line like this one. So, this slope here, that is going to, that is indicating the beta 1, and this here interceptum, that is indicated by this beta 0. So, now here this beta 0 and beta 1, they are called as the parameter of the model, right. So, this beta 0 and beta 1, they are actually called regression parameters, right. So, now since we have obtained the paired observation, and suppose we have obtained small n number of observations, right. It is something like this, that you have here quantity of fertilizer and here output, that is the yield. So, you try to give say 1 kilogram of fertilizer, suppose you get 5 kg of yield. So, this 1 kg of fertilizer will be denoted as is say here x1, and this 5 kg of yield is going to be denoted by say here y1, and similarly if you try to take suppose 3 kg of fertilizer, then it is going to be indicated by x2, and suppose you get here 8 kg of yield, then y2 is going to be like this, and so on. Similarly, you have here such an observation. So, this is what we mean by the paired observation. So, now obviously you need to assume that each of this pair of observation is satisfying this linear model. So, we try to write down here that small yi is equal to beta 0 plus beta 1 xi plus epsilon I goes from 1 to small n. Now we want to apply the principle of least square, right. Actually, just for the information, you can also use here the method of maximum likelihood estimation to estimate the parameters beta 0 and beta 1. But in that case, you need to assume that the random errors are following a normal distribution, and they are IIDs, right. But anyway, means I am going to use here the principle of least square, and the good part is that that is just for your information. I am not going to do here that if you try to obtain the estimates of beta 0 and beta 1 by the principle of least square and by the method of maximum likelihood, both are going to be the same. So, that gives me an idea that unless and until I am concerned only with the estimation part, I have no issue in considering either the principle of least square or method of maximum likelihood. Well, in case if I am going for the construction of confidence interval, test of hypothesis, then definitely I need to assume that epsilon i's are following a normal distribution with mean 0 and variance say sigma square. Right. So, anyway, now we let us try to concentrate on the principle of least square, for which I try to minimize the sum of squares due to random error for this given unpaired data sets on xi and yi. Right. So, now I create here a function say s beta 0 beta 1, which is equal to summation I goes from 1 to n epsilon I square. Now, this epsilon, because you have here yi is equal to beta 0 plus beta 1 xi plus epsilon I. So, this epsilon I can be written as yi minus beta 0 minus beta 1 xi. Right. So, this value can be written over here and we get this thing. Now, you simply have to use here the principle of maxima and minima. Well, you see one thing I must clear that in the case of principle of maxima minima, first we need to differentiate the function with respect to the parameter, put it equal to 0, that will give you the normal equation. This normal equation is solved, and after that we try to find out the second derivative, and then we try to see what is the sign of the second derivative at the value which we have obtained from the after solving the normal equation. And based on that whether this value is positive or negative, we try to decide that whether the obtained value is minimizing or maximizing the function. But here means just to save some time, I am not deriving here all the times the second derivative, but definitely my advice is that whenever you are trying to use the principle of maxima minima, you must obtain the second order derivatives and try to show that whether that is achieving maxima or minima. Well, so in this case also where I have found this here mu, yes, means I would say that if you try to, I will write it in the red color, but if you try to find out the second derivative of variance of y bar star and with respect to du mu square, and try to put here the value of mu which you have obtained here as a minus xxy upon sx square, and then if you try to check the sign of this derivative, you can decide whether that it is really minimizing the value of the variance. So, similarly here also in this case, first I try to differentiate this function as beta 0 beta 1 with respect to beta 0 and with respect to beta 1, and we get here these two equations. So, these are your two normal equations. Now, you simply have to put them equal to 0 and you have to solve them, right. And the algebra is very simple. For example, I can show you from here that if you try to solve this equation, so try to substitute here, this will become I goes from 1 to n yi minus beta 0 minus beta 1 xi equal to 0. And now, if you try to see, you try to open it, summation yi minus summation beta 0 minus beta 1 summation xi equal to 0. So, now this is summation goes from I goes from 1 to n. So, what will now happen, that this will become here n times y bar minus n times beta 0 minus n times beta 1 times x bar equal to 0. And now, from here if you try to solve it, you get here beta 0 is equal to y bar minus beta 1 x bar. So, now you can see here that this depends upon beta 1. So, this beta 0 is going to be known if beta 1 is known. So, now the question is this, how to know this beta 1. So, for that I can consider this second equation, and if I try to solve this equation over here, then if you try to solve, this will give you beta 1 is equal to small sxy upon small sx square. So, now this becomes an estimator of beta 1. So, we try to denote it by say here b1, and once you try to substitute this value of B1 here in this beta 1, then I can write down this new value of beta 0 as a y bar minus B1 x bar, and this I am denoting as a here B0. So, this is exactly what I have obtained here. So, you can see here that this B0 is equal to small y bar minus B1 x bar, and B1 is equal to small sxy upon small xs, where sxy is given by summation I goes from 1 to n xi minus x bar yi minus y bar, and sxx is simply here summation I goes from 1 to n xi minus x bar, and they all are a sample based quantity. And yeah, means after this, if you try to verify the second order conditions that you try to obtain the second order derivatives, obtain the second order derivatives of S beta 0 beta 1 with respect to beta 0 and beta 1, and if you try to verify, this will verify that B0 and B1 are minimizing this S beta 0 beta 1, right. So, that you can obtain. I am not doing it here, I am skipping it. So, what is your S beta 0? This is your this function here, right. This is your here this function. Okay. So, now you can, now if you try to observe how does this small sxy upon small sx looks like. Means if you simply try to replace this small sxy by its population value, that is corresponding value in the population, which will become here sxy, and try to replace this small sxx as a capital Xxx, right. So, this value of beta, I can say this is something like a corresponding value of population value in the the slope parameter in the line y equal to beta 0 plus beta 1 x plus epsilon in the population. So, now if you try to see what is this quantity, now if you try to look here what you had obtained here, I will try to write down this in blue color so that you can see here. What about this? This is not equal to something like minus times beta, right. So, now this is what I was trying to tell you, that if you try to use any of this methodology, you will have the similar things, okay. But then one should understand that how are you going to interpret it, right. So, in case if you try to club both these methodologies, you can see that the optimum value of mu is the same as the value of the regression coefficient of y on x with a negative sign, that is mu is equal to minus beta. And now, in case if you remember, you had considered the estimated y bar star, say here y bar plus mu times say here x bar minus x bar, or there we had taken say small x bar minus x bar, right. So, if you try to now replace here mu by here minus beta, and then you try to replace it by estimator minus E1, you get here this estimator y bar hat reg, which is equal to y bar plus B1 times capital X bar minus small x bar, right. So, now, but in this case you can see here when you are trying to replace here the value of here mu, then means at least theoretically I can say that you have two options. You can assume that whether mu is known or mu is unknown, right. So, in case if mu is known, then you simply have to keep here minus times beta, and if the mu is unknown, then you are going to replace it by minus times B1, right. So, this is what you have to keep in mind, so that and you don't get confused between the two terminologies, because sometime you will see people are using the term difference estimator, and sometimes they are using the regression estimator also in the context of a regression method of estimation. So, both are the same thing, and when we are trying to analyze the properties of this estimator, definitely means in order to have a complete overview, we will try to make two assumptions, or we will try to consider two cases when this mu is known and mu is unknown, and we will try to analyze its property. So, let us try to consider the first case, that suppose this mu is known. Well, saying that mu is known, that is equivalent to saying that beta is known. Beta is known means beta is pre-assigned. Pre-assigned means you know the value beforehand. So, the first case we are going to consider here is that the regression estimator with pre-assigned beta. So, suppose the value of beta is known as beta 0. Then this regression estimator will become y bar hat reg is equal to small y bar plus beta 0 times capital X bar minus small x bar, right. And yeah, it is possible that, for example, this beta is going to be the slope parameter. So, beta is essentially indicating the average change in the value of y when there is a unit change in the value of x. So, you can also see, actually, if you try to look into the model what we have taken, y equal to beta 0 plus beta 1 x plus epsilon, and if you try to take it expected value of y is equal to then it will become beta 0 plus beta 1 x plus 0. So, in case if you try to see this, the value, the partial derivative of expected value of y with respect to here x, this comes out to be beta 1. So, this beta 1 is going to indicate the rate of change in the average value of response variable when there is a unit change in the value of x, right. So, now this means, for example, you can think means if you go to a field and try to interact with the farmers who are cultivating the crop for the last couple of years, and if you ask them that, well, if you try to use this fertilizer in your this field, then what do you expect? They simply say, okay, we are using suppose 5 kilogram of fertilizer in 1 hectare. Now, in case if you make it 7 kilogram, then the yield will increase by say 5%, 10%, or the yield will become 8 kilogram. So, they have a fair idea that what will be the change in the output of the crop when there is a unit change in the value of the fertilizer. So, they will have a fair idea, and under those type of conditions, this type of estimation method what we are going to consider will be useful, that you know the value of beta 0. Okay. So, now let us try to find out its properties. So, we first assume that we have got a random sample, say xi, yi, I goes from 1 to n, and we have this estimator. So, now, and this sample has been drawn by SRS WOR. Now, you can understand that when we are trying to assume that the sample is drawn by SRS WOR, then definitely at various places, whenever you want to take the expectation or the variance, then you have to use the corresponding outcome. Well, in case if I ask you, suppose I decide to use simple random sampling WR with replacement, then what will you do? The entire algebra, whatever I have done, either in the case of ratio estimation or in the case of regression method of estimation, the steps and procedure are going to be the same. The only thing is this, wherever you use the variance expression, there you have to make the change. For example, you can imagine, or you can recall actually, that you have used expected value of epsilon 0 square, expected value of epsilon 1 square, etc. in the case of ratio method of estimation. So, now here you are going to use an appropriate variance expression which is based on simple random sampling with replacement. So, the same thing will continue in the regression estimator also. So, now in case if you try to find out the expectation of this estimator, this comes out to be expected value of y bar hat reg, which is expected value of y bar plus beta 0 times expected value of capital X bar, but this capital X bar is known, that is assumed to be here known, that is and that is actually a fixed quantity, right. This is known and fixed because it is population value. So the expected value of x bar will remain as x bar, and then we have expected value of small x bar. So now this small x bar is going to be the same as capital X bar. Why? Because you are using the simple random sampling, and in simple random sampling you know that sample mean is an unbiased estimator of the population mean. So now this term comes out to be capital Y bar. So one can conclude very easily that this Y bar hat reg is an unbiased estimator of capital Y bar when beta is known, right. Now in case if you try to find out the variance of this estimator, then the variance of Y bar hat reg is defined at expected value of the estimator minus its expectation, and then take a square. So now in case if you try to substitute all these values over here, you will get this expression small y bar plus beta 0, capital X bar minus small x bar minus capital Y bar. Okay. Now you try to combine these two together. So this will become here small y bar minus capital Y bar minus beta 0 small x bar minus capital X bar whole square. Now you try to open it. So this is the first term, this is the second term, and this is the cross product term. So now if you try to identify what are these terms, the first term is that if you try to take this expectation sign inside, then this becomes here variance of Y bar. Then beta 0 square, and if you try to take expectation sign inside, then this becomes beta 0 square variance of small x bar. And if you try to take, so now this becomes here, hence if you try to take out take the expectation sign here, then this will become here minus twice of beta 0 covariance between x bar and Y bar, right. Now you know all these values because you are trying to draw the sample by SRS WOR. So this variance of Y bar will become here n minus n upon capital N small n times SY square. So this I can write down as small f upon n SY square, right. So that's what I am trying to write down here. So this will become f upon n SY square first term, second term will become beta 0 square f upon n Sx square, and the third term will become minus twice of beta 0 f upon n capital Sxy. And if you try to take this factor f upon n outside, then inside the bracket we have simply Sy square plus beta 0 square plus into Sx square minus twice of beta 0 into Sxy, right. Now this Sxy can also be replaced by using the relation of correlation coefficient. Correlation coefficient is defined as rho is equal to Sxy upon say Sx Sy, right. So this Sxy can be written as rho times Sx Sy. So this is now the final expression of the variance of a regression estimator when beta is known, right. Beta is known. Okay, and then these are your expression for the Sx square and Sy square, and rho is the correlation coefficient between capital X and Y. Now an obvious question comes here that what was your ultimate objective? Your ultimate objective was not to use arithmetic mean or ratio or regression method of estimation. The ultimate objective was to estimate the value of the population parameter capital Y bar. So for that you have used different estimators. One among them is a sample mean, which is based on simple random sampling, and then you have based on the use of auxiliary information, ratio and regression method of estimation. So an obvious question comes in the mind of experimenter that whenever he or she has to do the sampling, which sampling method should be used, simple random sampling or this regression method of estimation. So in order to answer such a question, we try to compare the variances of regression estimator and the sample mean. So now comparing the variance of regression estimator with the variance of sample mean under the assumption that beta is known to us, we see that variance of regression estimator is going to be smaller than the variance of y bar if this condition hold true. You simply have to write down this variance, because variance of y bar is simply going to be your here f upon n sy square. And you can see here from this expression also, I will use here a different color, that this is your here the quantity which is your variance of y bar under SRS WOR. So now whatever, so if you try to take it on the left hand side, the remaining quantity here is this thing. So that is what I am trying to write down here, right. So this is the same quantity. So you simply have to now check the positivity or negativity of this factor, of this inequality. So now if you can write this equation like this, beta 0 into Sx square, and inside the parenthesis beta 0 minus twice of Sxy upon Sx square. Now we have to check under what type of condition this is going to be negative. So you can see here in this equation, this Sx square will always be greater than 0. This is always positive. Beta 0 is the intercept term, that when you are trying to plot these paired observations, then if you try to fit here a line, the line will go like this. So this is the part which is indicating the beta 0. So now you know that this part can be positive as well as negative, because in case if your regression line is passing through here, then this is going to be negative also, right, and this is the origin here. So this beta 0 can be positive, beta 0 can be negative, and as such it is lying between minus infinity and plus infinity, and this quantity inside this bracket also, if you try to see, this is positive, but this is your capital Sxy. This depends on the sign of the correlation coefficient. If x and y are positively correlated, then Sxy is going to be positive, and if x and y are negatively correlated, then Sxy is going to be negative. So now you have to think that under what type of condition this product of two part is going to be negative, right. So this part is going to be negative under two possible conditions, that beta 0 is negative and the quantity inside the parenthesis is positive, or this beta 0 is positive and the quantity inside the parenthesis is negative. So if you try to solve these two conditions, you get here that under the first situation, this beta 0 should lie between twice of Sxy upon Sx square and 0, and in the second condition, this beta 0 should lie between 0 and twice of Sxy upon Sx square. So yes, so beta 0 is an sort of intercept term. What is the meaning of intercept term? If you try to recall, you had this relationship y equal to beta 0 plus beta 1 x plus epsilon. So now if you try to take here expectation sign, then this becomes here beta 0 plus beta 1 x, right. So in case if I try to write down here, if x is equal to 0, then expected value of y becomes beta 0. What does this mean? So beta 0 is the average value of y when x is equal to 0. This means what? That in case if you don't give any input, then still there will be some output, and beta 0 is the average value of such an output. Now a natural question crops up in our mind when we are not giving any input on x, then how this output can be there? That is pretty simple. If you try to see, when you try to grow a crop, or even at your home also you try to grow a small plant, you try to put some seeds in the soil, and now you have two options. Either you try to give some additional fertilizer, or you don't give any extra fertilizer. The soil has itself own fertility. So in case if you don't give any fertilizer, then the quantity of fertilizer given in the outcome will become 0, and whatever the outcome you are going to get, that will be dependent on the soil fertility only. So in that case, whatever outcome you are going to get, that is going to be indicated by expected value of y, that is beta 0. Similarly, we also say that the income of a person depends on the level of education. So, definitely if the person is more qualified, we expect that the income or the salary is going to be higher. But does it mean that if the person is has no qualification, he or she is completely illiterate, the salary is going to be 0? No. The person can do something and in which that much education is not required, and possibly the person can earn something. So, in those cases, even if the level of education is going to be 0, the person will have some non-zero income, some positive income which is greater than 0, right. So, this is the meaning of this beta 0. So, now based on those conditions, you can verify this condition and you can decide whether you want to use ratio estimator or regression estimator. Now, second option is that you try to choose the beta such that this variance which you have obtained here, this is minimum. So, in order to use this thing, we try to use the principle of maxima minima, and we try to differentiate the variance obtained with respect to beta. So, if you try to differentiate here and put it equal to 0, you get here beta is equal to rho times sy upon sx, which is the same as say here sxy upon sx square. So, that was the value which I was trying to show you here, if you try to recall. Right. If you try to see here, I will mark this thing in red color. So, on this slide, when I was trying to introduce this least square estimation, there I shown you that this beta looks like as if this is the population version of this small b1, which is the least square estimator of the slope parameter, right. Now, after this you have to verify the second order condition also. So, you try to take out here variance of y bar here reg divided by d beta square, and try to put beta is equal to sxy upon sx square, and you will see that, and that this will provide you the minima. So, you can see that this value of beta is minimizing the variance of regression estimator. Okay. So, now this is the value which is optimized, minimizing it. But my question is this: what is the value of that minimum variance? So, in order to obtain the value of that minimum variance, what we can do, that we can substitute this value of beta in this variance. So, let us call this obtained value of beta as a beta optimum. So, beta opt. So, now we try to substitute this beta opt in the expression of the variance which is here, right. Yeah, there should be a factor of f upon n. So, if you try to see, I have written here, and I simply have replaced this quantity here beta square by this rho square sy square upon sx square, and this quantity here rho sy divided by sx here beta, and we try to simply solve it, and you can see that this quantity is coming out to be f upon n sy square and 1 minus rho square. So, rho is the correlation coefficient, population correlation coefficient between x and y. So, you can see here that the minimum variance what the regression estimator when beta is known to us can be like this. So, if so this tries to answer the question that when I say that beta is pre-assigned, that means beta is known to us. So, the question comes, different people will give us different values of beta. So, a natural question comes that which of the value of beta is going to give us the minimum variability. So, the answer comes out to be here, that if you try to choose the beta which is close to the value rho sy upon sx, then it is going to get give you the smaller variability, and the smallest value of the variability can be obtained when you try to choose exactly beta equal to rho sy upon capital Sx, and the value of the variance is going to be here like this. Now, in this factor, if you try to see what is this f upon n sy square. Do you remember what is the variance of sample mean of y in the case of simple random sampling without replacement? Don't you think that this is the same thing? So, now let us try to compare it. So, this is quantity is going to be simply your here variance of y bar under SRS WOR, right. This was capital N minus small n capital N small n into SY square. And this factor here is 1 minus rho square. Rho is your correlation coefficient, right. So, this rho always lie between minus 1 and 1. So, this rho square will always be smaller than 1, right. So, this quantity is going to be smaller than 1. Okay. So, once you do this thing, then you can see here that variance of y bar hat reg is always less than or equal to variance of y bar SRS under WOR. Well, that is our default assumption. So, you can see that in case if somehow beta is known to us, and that is known to us precisely 100% correct value, then this regression estimator is going to give you the better value than the sample mean which was obtained under the simple random sampling. But now I ask you one more question, that you are assuming that the beta is pre-assigned, that means somebody will tell you the value, and it may happen that value which you use that is not exactly to the value of beta optimum. So, now the question comes that what will be the difference, means if somebody wants to use here in a different way, right. So, the true value is beta optimum which is going to give you the minimum variance, but you are trying to use another value beta 0. Right. So, under this type of situation, the question is what will be the change in the minimum variance of regression estimator when there is a departure from the value of beta, that is from beta optimum you are trying to choose something else. Okay. So, now what we try to do, suppose the value of beta is known to us is beta 0, and this is suppose not equal to beta optimum. So, then in that case we try to rewrite the same expression what we had obtained for the minimum variance of this regression estimator and try to see what happens. So, the expression of the variance we had obtained was here like this, right. Now, in this expression I try to add and subtract here a term rho square sy square. So, this is what I try to do, and then I try to combine this term and this term. So, this will become here 1 minus rho square times capital sy square, and then all other terms are here, this one and this one like here. And if you try to simplify this term over here, this is simply your here beta 0 minus beta optimum whole square into Sx square. Now, you can see here that in case if you are somehow able to get the most accurate value of beta 0 which is the same as beta optimum, then this term is going to be 0. Right. And in case if the beta 0 value is differing from the value of beta optimum, this difference will increase. This difference increases as there is more departure. Right. So, now you have this idea. Now, we try to find out an unbiased estimator of this variance of y bar hat reg, that is the unbiased estimator of the variance of regression estimator. So, you know that you have obtained this expression, you can see here, right, which I am marking. This is the expression of the variance of regression estimator that you have obtained. So, now in case if you simply try to substitute the sample the population values by their corresponding values. So, we know because we have used the simple random sampling, the expected value of a small sy square will be equal to capital Sy square, expected value of small sx square that will be equal to capital Sx square, and expected value of small sxy will be equal to capital Sxy. Right. So, if you simply try to substitute all the respective values over here, or if you try to simplify this expression also, you can get an unbiased estimator of the variance of regression estimator like this one. Right. And you can note from this expression that from this expression what you have just obtained here like this one, which I just explained you, that the variance of this regression estimator increases as the difference between the beta 0 and beta optimum increases. Right. Okay. So, now we stop in this lecture. So, you can see in this lecture we have considered the case when beta is known to us, and we have analyzed all these properties. So, this type of analysis will give you an insight that if you know the 100% correct value, true value, then how the things move and how they will look like. Yeah, more interesting example will be where you don't know the value of beta and it has to be estimated from the sample itself. So, you know, now you have done such a case in the case of ratio method of estimation also, then the estimator of beta will become a random variable and you can do all sorts of analysis, algebra, etc. So, that we will try to do in the next lecture. So, I request you now that you please try to revise this lecture, try to understand the concept and try to do this algebra without looking into the notes, without looking into the slides. And you try to do it in case if you get stuck somewhere, then you try to look into the notes and slides and try to see what was the reason that we stuck there. That will help you in understanding this lecture in a much better way. So, you try to study and you try to practice, and I will see you in the next lecture. Till then, goodbye.